Okay, hi everyone, and welcome to the last gravity seminar of this year. Uh, so today's speaker will be Dina Meylakh from the Hebrew University. She will tell us about tidal response and thermodynamics of black holes. Please, Dina.
Okay, so hi, I'm Dina. I'm going to present to you work done jointly with Itamar Cohen and Israel Warshawiak, together with our advisor, Misha Smolkin. So first consider a Schwarzschild black hole. The Schwarzschild black hole follows the laws of black hole thermodynamics. So the zeroth law of black hole thermodynamics is that the surface gravity is uniform along the horizon. The first law is that the variation of the mass is proportional to the surface gravity times the variation of the surface area of the black hole. The second law of black hole thermodynamics is that the variation of the area of the black hole does not decrease, so it can only rise. And the third law is that the surface gravity cannot be reduced to zero within a finite time. So this is very analogous to just regular thermodynamics. If we think of the surface gravity as the temperature, the mass as the internal energy, and the area as the entropy. And then the second law of black hole thermodynamics is just like it's just like saying that the entropy can only rise. So throughout the talk, I'm going to use these variables, the thermodynamic variables and the black hole variables interchangeably. But what I mean by that is just the black hole variables and the black hole thermodynamics. Okay, so now consider taking the same black hole and admitting it in some background. So we're going to ask throughout this talk, what's happening with the first law? Will it admit any corrections? So we're going to parameterize our corrections with M and P, where M would correspond to information about the external perturbation, and P will correspond to information about the response of the black hole itself. So it would be the induced polarization. So, but first we have to understand how to quantify tidal response. So the way to do this is to just look far away and treat the black hole as a point particle with corrections. So the way this is done is by writing the point particle action and writing terms that correspond to the allowed symmetries. So the allowed symmetries are reparametrization invariance and general covariance. So reparametrization invariance just means that if we change our word line tau, we should have similar terms, and general covariance is just changing our coordinates should still yield the same terms, and so all the indices should be contracted. So as you can see here, this is very analogous to the electromagnetic multiple expansion, where on the first term we have a monopole, on the second term we have a quadrupole. This is because gravity, there is no negative charge for mass in gravity, so there is no dipole for gravity. So we have to start from the quadrupole, and we can see that the fields are very much analogous to electromagnetism. So if you recall in electromagnetism, the electrostatic field is just the zeroth component of the field strength tensor, which is just like contracting it with a unit vector in the right direction. And so we can see here that gravitationally, this is very analogous. If we are at the world line and our x dot and we're in the center of mass, and our x dot is just a unit vector. This is just like contracting the Riemann tensor and getting a field. And similarly for the magnetic part, in electromagnetism, we contract the field strength tensor with a Levi-Civita tensor. And here, similarly, for the gravitational part, we contract it with a Levi-Civita, the Riemann tensor with a Levi-Civita tensor. Okay, so the coefficients guarding these terms are going to be called love numbers, and I'm going to expand on them on the next slide. So if we assume that the black hole is stationary and the perturbation, the background perturbation is weak and also stationary, then it is very comfortable to work in the energy decomposition, a metric reparametrization that looks like this. So this phi field is a scalar field, and this AI field is a vector field, which is just like in electromagnetism where we have phi and A. But for gravity, we also have this tensor field gamma ij, and sometimes it's more comfortable to work with sigma ij, which is just gamma ij minus delta ij. And so we can rewrite our point particle action from before with these fields and get the following formula. So we can see now that these terms look just like just derivatives of the potentials, and just like the electric field and the magnetic field. So F here is dA minus dA, just like the field strength tensor for electromagnetism, but with this A this time. And these are the gravitoelectric and gravitomagnetic love numbers, which we saw on the previous slide, but on the previous slide we just saw for L equals 2. This is the generic for all terms that are that have two field insertions. Okay, so in this talk we're going to have two goals. The first goal is to calculate the love numbers directly in a gauge-invariant way and a new way. And our second goal is to correct black hole thermodynamics with these love numbers. So before starting our first goal, let's consider a simpler example and consider a conducting sphere. Okay, so let's write an effective point particle action for this sphere. And so we recognize the first term. The second term is just the monopole with the charge. So let's assume for simplicity that the charge is 0 and look at the other terms. So alpha here is just the electric susceptibility and beta is the magnetic susceptibility. So we want to calculate alpha, and in this example, we want to calculate alpha. And so we decompose our metric, our field, electromagnetic field, to A0 and AI, and we assume it's static, so AI equals 0, and we focus on the susceptibility calculation. So our EFT, our effective field theory action, looks like this. And now we put the conducting sphere inside an electrostatic background. So the background is going to be symbolized with a bar, and it's just a constant electric field times some coordinate x. And we plug this in the effective field theory, and we expand, and we get interaction terms between the field and the background field. Okay, so we have this. So we have an effective action. So the first thing we do when we have an effective action is write Feynman diagrams. So in this diagram, the double line corresponds to the particle's world line. The X corresponds to a background insertion, and the full line corresponds to the propagation of the field itself. So we just take the vertex from the second term between the field and the background field, and the propagator from the first term, and we compute this correction to the field. And so our full EFT field composed with the background field and this correction that we calculated is the following. But this is a pretty standard setup, and we just know how to calculate the equations of motion. And so we calculate the equations of motions directly and compare our results. So when we compare, we can see right away that alpha is just 2 pi rs to the third, where rs is just the radius of the conducting sphere. So we calculated alpha, hooray. But was this in a gauge-invariant way? No, because both the equations of motion solutions and writing Feynman diagrams are generally gauge-dependent. So this was the way the love numbers were calculated traditionally up to this point in the literature, but we're going to do this in a different way. So consider again the conducting sphere and an electrostatic background. Write the full action and the full solution, and plug in the full solution into the full action. Now keep only the terms that correspond to the finite terms that correspond to the external field E, and rewrite them so they match just the derivative of our background field. Now inspect our effective field theory action, and we see a term matching this exactly. And again, we can see that alpha is 2 pi rs to the third, just like before. Was this in a gauge-invariant way this time? We'll say that yes, because the action itself is a gauge-invariant quantity. And so comparing the actions, we don't have to specify gauge, and we can just say that this coefficient this is its value without a gauge, without specifying a gauge. So another way to view this calculation is to think about scales. So if we think about it, alpha encodes just in the inner structure of the conducting sphere. So it's like thinking that it encodes the short wavelength modes of the field. While a bar, the external background, it encodes long wavelength modes. So the full action should include both.
May I ask a question?
Yes.
In what sense the external field is gauge invariant? The gauge, this is like a boundary condition, so it's unclear to me what is the relevance of gauge transformation on the external field. Can you explain?
Where on which part?
So, for example, if I put an electric field, an external electric field, I have to specify its, for example, the vectorial character, direction, for example, of the external field. And if I do a gauge transformation, that external field will change. So,
That's right. But when you
so typically, so I don't understand in what sense terms that involve the external field are gauge invariant.
So you are correct. But once you identify your external field and write the full action in the form of just derivatives of the external field as if you never specified a gauge, then this becomes back gauge invariant.
Dina, I think you should probably say that the electric field is a gauge invariant quantity because it's a field strength tensor, so it is gauge invariant. So the field, the phi, the scalar potential or the vector potential in general is of course gauge dependent. It changes if you choose different gauges. But the electric field, so the final expression depends on just external perturbation, which is expressed in terms of electric field or magnetic field. This is a gauge invariant quantity, so it's physical. So therefore, what you calculate, you basically calculate gauge invariant object action in terms of gauge invariant external fields, electric and magnetic fields. In the case of gravity, these external electric and magnetic fields are replaced by external curvature. So the background will be curved, and the external curvature is again a gauge invariant quantity because it's curvature.
Yeah, I think I understand, but in specific situations, this electric field, for example, is fixed.
Yeah, and it is gauge invariant, right? Because it's a
Okay.
physical field.
Okay, I understand that. It might have been easier if this were written in terms of the F mu nu, and then it would be clearer. I think it's possible to do that.
So here E is F0I, 0I.
Exactly. Yeah.
Right.
Okay. Very good. Okay. Thanks.
Okay. So okay, the full action should include both the short wavelength modes and the long wavelength modes. And so writing it this way can be seen as just integrating out the short wavelength modes. Okay, but let's get back to our goal. And now we're ready to write the action as now we're ready to take on gravity and write the exact gravitational action. And so the exact gravitational action is given by this, which has two terms, the Einstein-Hilbert term, where R is the Ricci scalar, the Gibbons-Hawking-York term, where Bk is the extrinsic curvature and little h is the induced metric, and a matter action. If our background field is a matter background field, we have to specify its action. So the Gibbons-Hawking-York term is supplemented, so the equations of motions would only depend on first derivatives and not further up. And okay, and so unfortunately, we have no full solution for the gravitational problem with our Schwarzschild black hole in the background. So we have to proceed perturbatively. So we write our metric as the Schwarzschild metric plus perturbations. And instead of plugging it in the full action, we perturb the full action around the Schwarzschild black hole. And so we vary the action the first time, and we get this nice expression. And then unfortunately, that's not sufficient for our needs. So we have to vary it again, and we get this now impressive expression. And unfortunately, this is sufficient for our needs. So it's time to talk about the different backgrounds we're going to embed our black hole in. So just a reminder, the energy decomposition is given above. So there are two families of backgrounds we're going to consider. First, the gravitational backgrounds, where the matter action is 0, and the matter backgrounds, where the matter action is not 0. So for the gravitational backgrounds, we're going to consider the gravitomagnetic field, where only the vector field is turned on, and it has this like the spherical harmonic resembling function. And similarly, a gravitoelectric background, where only the phi field gets a value, and it also looks like a spherical harmonic. And the matter backgrounds, we consider a minimally coupled scalar field, and a Maxwell background, which is where we assume the background is static, so we go and to our electrostatic field.
Dina,
Okay.
can I ask a question? So there, you made an assumption of that the background is static.
Yeah.
Is this essential to make this assumption? Can you go? I mean, does your method work also when you go beyond this static background?
So not exactly static, stationary. So the gravito-magnetic background does
Yeah.
mix with dt, but no, only stationary background. We consider only stationary backgrounds, and you have to do a lot of work to expand this further to dynamical backgrounds.
Okay, but so it's in principle it also could work, but it's just more elaborate.
Have not been done by us.
Okay.
So how can I try
Yeah.
to answer this question?
Sure.
So what you have to do if you want to do time dependence, Shanib can probably tell you more, is that you remember the Green's function that he was using initially for solving that. So you have to expand that to write the full Green function and expand that in time derivatives. But so probably this can be, so there's no fundamental limitation in including time dependencies. It just becomes more complicated, but probably it will be in terms of time derivatives of the fields that they use. So
Okay. Thanks.
Yeah, thank you for this clarification.
And just one more comment. Since Dina is going to discuss thermodynamics, so of course for thermodynamics we need only stationary solutions, right? Because otherwise the system is not in equilibrium. So for thermal physics you don't actually need anything else beyond it. But okay, for time-dependent cases, of course, they are also very interesting, and this is a different beast.
So obviously, I agree.
Okay, so we have the backgrounds, and now we're ready to evaluate the full action. So for simplicity, I'm going to focus here on the gravitomagnetic case because it's the simplest one, but if you are interested in the details, the rest are in the paper. So thankfully, the full solution has been calculated already in the literature.
And Dina, may I stop you? So can you just say in a few words, what is the purpose of your calculation? What are you going to show?
So as you remember that we did in the warm-up with the conducting sphere, we're going to recalculate the love numbers, but this time in a gauge-invariant way.
I understand that, but is there going to be something related to black hole thermodynamics at the end?
Yes, this would be our second goal. And right after we complete calculating the love numbers, we're going to move on to the thermodynamics.
Okay.
Okay. So thankfully our exact action has been calculated. The solutions to the equations of motion have been calculated already by HUJI et al. and Haddad et al. So we supplement this with boundary condition, and we're ready to plug this into the full action. So we massage this action so that our boundary is far away, and we look at it as if it's a point particle, and when we obtain a term that looks like our point particle action. And so we can identify our gravitomagnetic love number, which agrees with the literature, but this time in a gauge-invariant way. So we have completed our first goal, and we can move on to the next goal. So let's discuss the free energy F. Luckily for us, the free energy is just the full action on shell. So we have calculated this in the previous slides, and we know the love numbers, and we can just take its value from the point particle action and get it straight away. So F is the Legendre transform of U and TS, and so it will help us correct the first law at the end. So let's now talk about the internal energy U. So okay, so the definition for the energy U is given to us by Weinberg in his book Gravitational Cosmology, and a similar derivation can be found in Landau and Lifshitz. So the question is, how do you define the energy U for a curved spacetime? So you have to assume that at large distances, the metric approaches a Minkowski metric. So we parameterize our metric as just a Minkowski metric plus some addition, where only far away we need it to be small. So next to the black hole or next to the system, it can be large. And we can define a total energy momentum pseudotensor tau mu nu, where big T mu nu is just the regular matter stress energy tensor, and little t mu nu would be the gravitational energy momentum tensor. So T mu nu is defined as just taking the equations of motion and subtracting the linearized equations of motion, where the linearized equations of motion are, where the linearized Ricci tensor is just the part of the Ricci tensor linear in this correction delta G mu nu. Okay. So what's so interesting about this tau? This tau is conserved in the ordinary sense. So the derivative of tau is 0. This is due to the linearized Bianchi identities, the same identities that make the covariant derivatives of big T mu nu 0, this time make the regular derivatives of tau be 0. So we can define our momentum pseudo vector, which is just the integration over the tau, and take its 0th component to be the internal energy U. And through Gauss's theorem, we can take the volumetric integral and span it on the boundary, which is great for us because if we convert it on the boundary, then our point particle approximation is enough, and we can treat it as a point particle with corrections. Okay, so all we need is just the corrections to the metric on the boundary.
Can I ask another question? Sorry for that. So Thorne, for example, suggests that the energy be defined because you're working with in weak field. So you take the original mass and you compute the work that would have been needed to polarize the object. So it's like a PDV or something like that. And I was wondering whether your definition and that definition coincide.
Unfortunately, I'm not familiar with that definition.
So in the usual case, suppose that you have an object and you perform some work on it, then its energy changes. So you can imagine that you increase the external field, it performs some work on the object,
Yeah.
and its energy increases. And this would be now the calculation for the new energy.
So we definitely interpret our results in this way.
But can you check, did you check whether if you actually do that calculation of the work, you get the same answer as with your pseudo tensor?
I didn't check, I'm sorry.
Okay. Thanks.
Okay, so what are the corrections to the metric? So for that, we go back to the effective field theory we discarded before, and we do specify an effective field theory action, an Einstein, which is composed by the Einstein-Hilbert action, the point particle action, and a gauge fixing term. So you can see the gauge fixing term is just chosen to be like a linearized harmonic gauge, or if you are familiar from electromagnetism, there is the Lorentz gauge for A, and another condition for the tensor field. Okay, so we have an effective field theory action, and so we can write the Feynman rules and write down the propagators and the vertices and calculate all our calculations. So I'm not going to write all the Feynman rules, but let's see how this works for calculating the energy for no background. So for no background, the only part of the point particle action that's relevant to us is just the monopole master. And so we can write the Feynman diagram, we can write the vertex M phi and add it to the propagator you see in the first line of this slide. And we get a correction, or we just get the phi field, which is the Schwarzschild metric. We plug this in our equation for the energy, and we just get M, the internal energy of the Schwarzschild black hole as we expect. And so we do the same procedure for all the backgrounds, the gravito-magnetic and the gravito-electric. Again, the double line corresponds to the black hole world line. The x's correspond to background insertions, and the full line corresponds to the phi field. The squiggly line corresponds to the sigma field, and the dashed line corresponds to the vector field AI. So we stop. Because we do everything perturbatively and we have to stop at a certain order, we do this for the dominant parts, and we stop at 2 background insertions, and we do everything for L equals 2. And similarly, we calculate the energy for the scalar background and the Maxwell background, and we get all our energy corrections. So, as I promised you, we're going to extend the first law of black hole thermodynamics with this parameterization of M and P. But all we calculated this far was U, the internal energy, and F, the free energy. So how is that going to give us P? So for that, we're going to use the fact that the equations of motion are scale invariant, and we're going to check how all the thermodynamic quantities change when we change the scale. And we're going to plug them back inside the corrected first law. First, we're going to take lambda, the expansion parameter, to be 1 plus epsilon, where epsilon is very small, and compute the variations. And now we have the variations, so we can plug the variations into the first law and get an integrated version of this first law. Now we use that F is the Legendre transform between U and TS, and we get an expression for M times P, just depending on F and U that we calculated in the previous slides. And so we identify M with just the derivative of the potential, or like the analogous derivative of the potential minus the derivative of the potential, and which is just the amplitude of the waves that we put in. And we can then extract our polarization from that. Okay.
So can you go back to the previous slide?
Yeah. This
Can
one?
you explain why is it that you have to use this procedure and not just take a derivative of u with respect to m at fixed s in the usual way that we do thermodynamics? You have, right? You have the dependence of u on the external field.
So yeah, so even in regular thermodynamics, we use like Euler relations to separate the extensive variables from the intensive variables. And a similar treatment can be seen there too. But specifically here, to answer your question, we never calculated how the area changes or how the action or how the entropy changes. So
But you have to, the definition of of P requires you to fix S,
uh,
right? If I want to calculate delta P, then I calculate delta U, delta M at fixed S, and I get P, or delta P.
so yeah, you could do that, but you could also do what we did, where we kind of avoided that problem.
And how did you how did you make sure that you are doing it at fixed S?
So we just used a symmetry of the equations of motion, and plugged in. We computed the variations. So this is so.
Dina, perhaps I will help you a little bit.
Yes.
So
I'm sorry, but this is I'm really interested, so I want to
yeah,
understand.
sure. So first, again, so there is a we are looking at Einstein equations of motion, which are scale invariant, of course. If you do just change x, rescale x, right? If you rescale x, so equations of motion, this overall rescaling drops out, and equations of motion
Yes, I agree.
do not change. So that means, what that means? It means that if you found one solution, you can rescale x of this solution and get another solution. Or in other words, you can rescale parameters of your solution and get another solution. I think we understand that this is what happens.
Absolutely.
So what are the two parameters that we have in our solution? The two parameters are just mass of the black hole, because that's what we have, Schwarzschild black hole, and perturbation Q, right? So therefore, and basically rescaling of these parameters is completely fixed. When you rescale x by lambda, it's you know the rescaling of this scaling of these parameters just by dimensional analysis, right?
Yes, I agree.
So what Dina has here, U, S, M, and P, just based on dimensional analysis. So this is how these parameters like mass of the black hole, entropy of the black hole area, and the polarization change under this scaling. Okay.
Yes, I understand that. So in this context, it's just a question of how do you fix it?
Right, just on. So therefore, once you know this scaling, this is what basically SMAR, I'm not sure if, yes, SMAR formula. This is what SMAR did for us. It says, well, if we do this scaling, and let's assume that lambda is small, close to 1. So lambda is 1 plus epsilon. Okay. So then under the scaling, you know how your parameters of your solution change. You know how the area changes, right? Because if lambda is 1 plus epsilon, you just expand.
I understand all of that.
Right.
Yes.
So since this change is basically dimensional analysis, and it's infinitesimal change, and this family of solutions should satisfy this first law of thermodynamics, right? This du equals TdS plus mdP, what we
Yes.
have in the right corner. So you can just plug in these changes, these small changes, and check what you get, right? So you can just,
Okay.
so if you plug
So
in,
instead of fixing S, you just vary all the quantities and
exactly,
you
you change,
identify how each term
absolutely,
varies. Okay,
absolutely. So you
I
just,
understand.
in other words, you just follow the family of solutions parameterized by two parameters in this
I
case.
understand.
Okay,
Okay,
and of course, in general, if the system was not scale invariant or scale covariant, you would not be able to do it. But here, it's all based on basically fixed by dimensional analysis, and therefore, out of this differential form of first law of thermodynamics, you get integrated form of first law of thermodynamics.
okay. I understand that. Since you are talking already, maybe you can answer my previous question whether this definition of U is the same definition that you get from the work that the
Okay,
external
so
field does.
well, you see how we were looking for a quantity that is conserved. Okay, so in other words, a quantity that respects translation in time. So when you have the symmetry in time, right? Everything is static, stationary here. T, you have the shifts in time, and then the question: what is the associated conserved charge? So to me, the most natural, once you have this translational symmetry, you have some kind of netter charge. And this netter charge associated with translations in time is nicely fixed by this pseudo tensor.
Okay, thanks.
So, of course, as usual, pseudo tensor is not a true tensor, and therefore there are all kinds of subtleties associated with gauge invariance of these objects. Okay, so you could raise the same question in the case of Schwarzschild black hole, because for the Schwarzschild black hole you can also define this U using this pseudo tensor, and then so you calculate, you get mass, and then the question whether this energy, in what sense this energy is sort of gauge invariant, in what sense it's a scalar. And then there is this usual story that if you restrict your calculations to family of gauges that decay sufficiently fast at infinity, then the quantities that you calculate, this mass, is gauge invariant. So we basically use the same logic. So in other words, the quantities that we compute here is gauge invariant, provided that the gauges are decaying sufficiently fast at infinity. That's the point. Okay.
Thanks.
So the short answer to the question is that we do not calculate this U from this work principle, how much work how much energy you spend on polarizing your black hole. We just evaluate an object that is conserved due to this netter charge associated with translational symmetry.
Yes, absolutely. I am just saying that it would be interesting to compare.
Yeah, I understand, but this is not what we did.
Okay, thanks.
I want to add one more comment about the SMAR formula, which, as discussed already, is the integrated form of the first law. This is essentially known as Euler's identity for homogeneous functions, that relates the value of the function with the dot product of its gradient with a space vector. So it essentially goes to that, to Euler's identity for homogeneous functions. And the two are equivalent, the integrated and the differential forms.
So yeah, thank you for all the comments. Okay, yeah, so we completed our second goal. So all that's left is just to do a recap, and we can talk about more questions if you guys want. So let's recap. We started from a Schwarzschild black hole. We induced some background perturbation to it. Then we looked far away at this black hole and treated it like a point particle with corrections. Then we inspected the full action, and we got it to look like the point particle, the full action far away, and then we got it to look like the point particle action, so we could identify the lab numbers. Then we used the fact that the free energy is just the full action on shell, and then we wrote the effective field theory action, from which we computed the internal energy U. We then used the fact that the equations of motion are scale invariant to get m times p, and correct our first law of thermodynamics. So yeah, so that's a recap. We can talk more about questions if you guys want, or there's a discussion that I've prepared, whichever is preferred.
I can make a comment if it's time for a discussion.
First, we have to thank the speaker.
Yes, I don't know if it's the end of the talk or not.
Yeah, so is it the end of the talk? You said you prepared the discussion, so is it part of the question session, or how do you want to do it?
Okay, let's do the discussion. It's gonna open up more questions. So if you have questions,
But maybe if Barak has a question now, that it's all
yeah, let's do
it's
questions.
possible. Okay.
Okay, it's not a question, it's a comment, and it's about the electromagnetic preliminary that you did. You found that this coefficient alpha there of the dipolar kind of love number was equal to 2 pi r cube. So I want to comment first that this can be written as 3/2 times the volume of the sphere. So at first I recalled the r cube, but I didn't recall the 2 pi. But there's a nice way of describing it in terms of the 3/2 times the volume of this conducting sphere. And secondly, this has some relation with the problem in potential flow in fluid dynamics. If you put a sphere inside the fluid, then it's very similar to the electromagnetic problem, only the boundary conditions, instead of being Dirichlet, turn out to be the Neumann boundary conditions, I believe. And there one gets that there is an effective mass to the sphere, which is not 3/2, but 1/2 times the volume times the mass of the expelled displaced fluid. So it's a little bit reminiscent of the Archimedes effect. The sphere acquires an effective mass, which is 1/2 times the mass of the displaced fluid. So it's a comment.
Interesting.
So shall we continue, Dina, with
Okay.
your discussion, or what do you say?
All right. If no one wants to add any more questions.
There will surely
I
be
do
some
have a
questions,
few
but we
questions
can
about.
wait. Yeah. Okay. Go
Can I
ahead.
ask a question about the first result with the gravitomagnetic love numbers? Can you go back to the slide?
Yeah.
First, I wanted to clarify. You only have two scales here, right? You have the faraway scale and the Schwarzschild radius scale. So you don't have any other scale for the background perturbation.
No, we do it. The amplitude of the background perturbation is given here by C. So yeah, it's an unfortunate coincidence that for the gravitomagnetic we also use C for the background amplitude and for the love number, but they mean different things, and you can distinguish them by the indices.
Mm-hmm.
Yeah.
So what is this R that is way bigger than RS?
So we have to look far away to treat the black hole as a point particle action. So specifically, R is just our boundary. So where our boundary conditions lie.
Okay, and in the analogous problem from electromagnetism, you said that these coefficients store information about the internal degree of freedom. How can we see this here in this result? It's kind of hard to follow the definition of B and
So similarly as before, like alpha was proportional just to the conducting sphere radius at the end. So that was the internal degree of freedom. So here again, you can see that the only non-constant factor is just the Schwarzschild radius here.
And this is the same result just in the gauge-independent technique, right?
Right.
So this is in general dimension. What can you say like how can we see the behavior for d equal 4?
Yeah, great question. So for d equals 4, the love numbers vanish. So for a Schwarzschild black hole, all the gravitoelectric and the gravitomagnetic love numbers are known to vanish identically. And
Okay.
yeah, does that answer the question?
Sorry, just the last question. You can describe the Feynman diagram that you used for this calculation?
Yeah, of course. Right, so this is the gravitomagnetic Feynman diagrams. So the double line corresponds to the world line. And so any interaction with the world line can either be with our magnetic love number or with the mass m. So here we focus on the interactions that correspond to the magnetic love number. And you see the x's are the background insertions. So here, like, let's focus on this diagram. This corresponds to two background insertions interacting with the black hole and correcting the phi field. So we can attach this to a propagator and just calculate the correction to the phi field at any point in space.
Okay. All of these are of the same order, like dominancy, or
Yes. So you see that they are all up to two background insertions. So
okay, thank you. And thank you for the talk. Thank you.
Any more questions at this point?
I can ask
Can
a
you comment?
question.
Can
You
you
ask?
comment about?
Yeah. Sorry. So I wait.
Can you comment about a prospect to measure the love number in nature or get constraints on the magnitude of the love number?
okay, great question. That's the discussion. It's somewhat adjoined to the discussion I've prepared. So let's go back to it. Okay, so consider a Schwarzschild black hole. So from the second law of the black hole thermodynamics, we know that the entropy always rises. So for a Schwarzschild black hole, this corresponds to the area, which is proportional to the mass squared. Okay, so if we consider a black hole merger with M1 one black hole and M2 a second black hole going into M1 plus 2, this gives us a lower bound for the mass of the remnant. But we also know that from energy conservation, the mass of the remnant can't be bigger than the sum of the masses. So we have both lower bounds and upper bounds of the of the mass of the remnant. And now consider that the black hole is embedded in some background. So both U and S are going to get polarization-induced corrections. So these corrections, we calculated them for U in this talk, but for S, we almost calculated them. We have the variation of T times S. So disentangling the two is definitely a future direction. And another future direction is generalizing this whole discussion for Kerr black holes, which are more common in nature. So we don't know. So just by inspecting mergers and looking at the mass and the energy that is conserved or not conserved, we can now put bounds with the love numbers calculated, assuming we generalize this to Kerr black holes and we know the background. So it's far away, but it's I believe within reach.
There's a possible issue with that because when in mergers they emit gravitational waves, and I think that the pseudo tensor that you used is a little. I mean, there's an issue of whether it applies to situations where you have gravitational waves related to what Misha said about the decay at infinity. So that's one comment. The other is a question. So there are attempts already to follow the area law throughout the mergers. And I was wondering whether your calculation is relevant in such a context.
Yeah, so as I said, now unfortunately we only know the correction to the temperature times the area.
No, I understand that, but here this would be a time-dependent situation where you have a merger and you identify, this can be done in numerical relativity, you identify the area of the common horizon and you attempt to see whether that area is increasing throughout the process. And what I was asking is whether your methods can be useful in this context.
So what we did here is only for stationary backgrounds and for everything stationary. So I guess if you could extend this to dynamical, then maybe, but I highly doubt it because as Misha said earlier, the laws of thermodynamics only work for the stationary configurations. But if you think of this example of two black holes going into another black hole and they were stationary before and they're stationary after, you can then kind of get information about the process without losing this stationarity assumption.
Rami, perhaps the short answer to the question, no. Okay, a work should be done to extend everything to time-dependent situations. But in principle, again, if you ask about evaluating, say, what people call dynamical love numbers,
Yes.
or stuff like that, then in principle, yes, because you can, in principle, it can be done, except that no one did it so far. Because what we do here, we evaluate the love numbers, stationary love numbers, by calculating action on shell. Because this is what integrating out means. When we say that we have an effective field theory, it means that we integrated out some short degrees of freedom. But what that means, integrating out short degrees of freedom in classical physics, it means that you basically evaluate action on shell with specified boundary conditions. So specifying boundary conditions, you can do it in stationary situations or in dynamic situations. And therefore, in principle, you can also get effective parts of effective actions that explicitly depend on time. But as
Yes,
of today, no one did it.
no, I understand that, but so what you're suggesting, if I understand correctly, is that if you are able to calculate the on-shell effective action in the situation where, say, a common horizon is formed, you should be able to provide the theoretical tool for comparing with numerical relativity that essentially measures the area.
Right, but I can tell you what's the difficulty. To evaluate action on shell, you need classical solution, right? Expression for the classical solution. If you do not have classical solution, then you cannot evaluate action on shell.
Yes, but you can get the classical solution you in any case get from the numerical result with some
If I combine two techniques, analytical tool with some numerical results, then in principle, yes, you can take the numerical solution and hopefully evaluate classical action on this solution, numerical solution. I'm just saying that as far as I know, it was not done, and there are all kind of technical issues on the way, I guess.
But in fact, I was talking to some people. This is something that they're now trying to do because it's something interesting and that can be checked whether the area increases throughout the merger. And from what I hear from you, it seems that the analytic input using some variation of your method could be useful.
Could be, I agree, but again, I'm just saying that we so far, unfortunately, we
No,
didn't do it.
no, I understood that. I understood that, but I think this is the as far as I know, the internal energy cannot be measured even in numerical relativity, but the area or the entropy can be. So it's to some extent it's a more interesting quantity.
I see.
Thanks for the explanation.
Thank you.
I also wanted to make a small comment and then a question. So a small comment about the observations. So here you're talking about the situation in which you have a merger which occurs in some external field.
Yeah.
But I thought that the main place in which people are trying to constrain, or maybe can try to constrain these love numbers, is during the in-spiral, right? So there's some black hole in the background of another black hole, and then somehow you have a situation in which this approximation still works well. Maybe they're still separated enough from each other. And then you can, I mean, these lump numbers should affect the trajectory, right? Of let's say a small black hole in the background of a larger black hole. Right? So
Yeah.
that's a different kind of situation. And I don't know what's the status of testing this already, but
Yeah, I agree. This is different.
and it seems a bit more, I mean, because this scenario, like astrophysically, you're thinking about a merger which occurs, maybe a stellar mass binary merger happening in the background of a supermassive black hole or something like that. Maybe there you can get something like what you're discussing.
Yeah, or just like well, with the pulsar time arrays, they claim there is some gravitational background. So if it's weak enough, then that's good for us and for our approach. So
It's surely weak enough, but maybe it's too weak.
Maybe.
Why not just LIGO? Why not just LIGO?
So we need to know something about the background field. So
Yeah, but I mean, I'm saying about just the induced deformation, like, one of the black holes deforms the other. They both have a tidal deformability. So it's a small effect, but maybe there's sensitivity in it.
This is 5 p.m. and even the calculations of the standard without love have not, they're only now reaching 5 p.m. So it's really a major challenge.
Yeah, okay. So that's one point, but the question is if the experimental sensitivity is there. Because if it's there, then the theorists just need to work harder.
So the short answer is that no.
Okay.
I actually have a plot from LIGO if you want. There's so I just took this LIGO data from the web. I actually wasn't planning on showing this, so I don't even remember which exact Excel I used. But the gray area is just the error bars on the masses.
Okay.
So yeah, so here I plotted just I divided everything by M1, and I plotted the lower bounds of the entropy and the upper bound of the energy and the remnant black hole. So you can see that we can't really say anything.
Right. Yeah, no, but that's a zeroth order way of constraining it. If you describe the dynamics can be influenced by the tidal deformability of the two black holes, and then it's a question of, okay, Rami is saying it's a 5 p.m. effect, so it's hard to calculate, but then the question is whether there's a way to extract from the data, given that, let's say, the theorists know to calculate any loop they want. So I think that question still stands, and I bet it has an answer. Like, just have to open one monster paper of one of the detectors and see.
I'm afraid that you have to know to what extent the actual theoretical, it's like a background in the LHC, right? If you don't know the background, you cannot estimate the sensitivity for detection.
Okay, then that's a good question.
Okay, another question that I had is going beyond the linearized approximation. Is that feasible? Is that interesting? What was it explored already? Anywhere?
So we did this linearized approximation because this one wasn't explored. So
Okay.
definitely the next orders are there, and it would be interesting to see them.
No, because you need classical solutions, and there do exist some classical solutions, exact solutions of black holes in external fields. So and that's like an exact solution to any order in G. So I don't know, maybe it could be somehow helpful.
Yeah, definitely. Misha, would you like to comment?
Unfortunately, I can't add much. I think love numbers recently were explored beyond linear response. People basically argued that love numbers, including nonlinear love numbers, vanish to all orders in 4 dimensions. I don't think that there are closed form expressions for love numbers in higher dimensions. For nonlinear love numbers in higher dimensions. I don't think that such expressions exist. But in 4 dimensions, we know that they basically all vanish, including nonlinear. Now, regarding thermodynamics, well, I think there are no results beyond leading order correction. And of course, it's super difficult to prove, to do this thermodynamics non-perturbatively, right? So this is all I know.
Thanks. Yoav, you had a question?
Well, it's related to your question, which is what is the computation of the higher love numbers, this additional Wilson coefficients in the three dots that Dina wrote? But I guess it's not very important given that we don't know how to go beyond the linear order.
Yeah, it's hard. I mean, again, if we stay in 4 dimensions, then unfortunately, there is no question because all love numbers vanish. If we consider black hole in general number of dimensions, then little is known there. I mean, even just closed form expression for love numbers do not exist.
Misha, you now agree that in 4 dimensions also the nonlinear love number vanish because you were skeptical when we last talked about it.
No, I'm not skeptical. I think there is a lot of evidence, let's say. I mean, it depends on your standards of what proof means, but there is a lot of evidence that nonlinear love numbers vanish. I'll remind you, when I said I'm skeptical, I said that I'm skeptical that black hole does not respond at all to any kind of perturbations. But we know, for instance, from recent results that dynamical love numbers do not vanish. So there is something. So black hole does respond. It would be hard for me, at least, to imagine that it just does not deform at all under any kind of perturbations. But again, based on recent results, we do have dynamical response. So that's already something. And I think this recent paper by Para Martinez, I think they actually provided quite a nice. I think their proof is still questionable from a number of perspectives. Since that paper appeared, I looked at it more carefully. So there are questions about it, but I think it's a very nice paper, and they have their sort of convincing, to me at least, argument that love numbers vanish. But again, I still think there are some kind of loopholes in this paper. We can discuss it at some point if you wish. I can tell you what bothers me.
Sure,
I can give you a very simple argument why.
I have to go, Misha, I have to go so we can continue to discuss, and I want to thank Dina for the talk.
Yeah, thank you.
Bye.
Thank you for listening.
Okay, any more questions? Anyone? So if not, we can all thank Dina again.
Okay. Thank you, Dina.
Thanks for a great talk.
Thank you for listening.
Yeah, and see you all next year.
See you. Thanks,
Or
Shachar,
before
for
that.
organizing. כן, שחר, תודה רבה על הארגון.
תודה דינה, תודה
ועל
שחר.
יוזמה שממשיכה לאורך השנים. זה באמת לא מובן מאליו. אוקיי. טוב.
יופי, טוב, אז להתראות.
ביי.
ביי.